Welcome to this tutorial on C++ binary files. In this session, we will explore working with binary file input and output in C++. We will discuss key concepts and techniques to help you effectively handle binary files in your C++ programs. Let's begin by understanding the key differences between text files and binary files. In terms of storage format, text files store data as human-readable ASCII or Unicode characters, while binary files store data as a raw memory representation. When it comes to size efficiency, text files tend to be larger because each number is stored as characters, whereas binary files are smaller, utilizing the exact memory representation. For processing speed, text files are generally slower as they require conversion, but binary files are faster, providing direct memory mapping. Random access is difficult with text files due to variable record sizes, but it is easy in binary files with fixed-size records. Portability is high for text files, as they can be read across different platforms, but it is low for binary files due to endianness issues. Common uses for text files include configuration files, logs, and source code, while binary files are typically used for images, databases, and executable files. In C++, we use specific FileStream classes to handle binary file operations. The ifstream class is used as an input file stream for reading data from files. The ofstream class is used as an output file stream for writing data to files. The fstream class is a file stream that can be used for both reading and writing data. To open a file in binary mode, you need to use the iOS binary flag. This flag prevents any text transformations, such as new line conversions, and preserves the exact byte representation of the data. Here's how you can open binary files for reading, writing, or both. To open a binary file for reading, you would use std. ifstream infile.open data.bean std. iOS binary. To open a binary file for writing, you would use std. ofstream outfile.open output.bean std. iOS binary std. iOS out. For combined read/write access, you can use std. Streamfile data.bean std. iOS binary std. iOS in std. iOS out. When writing to binary files, several key functions are essential. The write function is used to write raw bytes to a file. The reinterpret_cast is used to convert data to a char asterisk, which is required by the write function. The size of operator is used to determine the exact byte size of the data being written. When writing data to binary files, there are some important considerations to keep in mind. Always check if the file has been opened successfully before attempting to write to it. Close the files when you are done with the write operations to free the resources. Be aware of platform-specific data sizes, as they can vary across different systems. Also, consider endianness for cross-platform use to ensure that data is interpreted correctly on different architectures. Here is an example of writing primitive types to a binary file. We first open a file in binary mode using std. ofstream outfile data.bean std. iOS binary. Then we check if the file is open, and if so, declare an integer and a double. We then use the write function, along with reinterpret_cast and sizeof, to write the integer and double to the file. Finally, we close the output file stream. When reading from binary files, there are several key functions to be aware of. The read function is used to read raw bytes from the file. The count function returns the number of bytes actually read by the last unformatted input operation. The EOF function checks if the end of the file has been reached. The reading process involves several steps. First, open the file with the iOS binary flag. Then, allocate memory for the data that will be read. Use the read function to load bytes from the file. Cast the data back to its original type using reinterpret_cast. Finally, check for any read errors to ensure that the data has been read successfully. Here's an example of reading primitive types from a binary file. We first open a file in binary mode using std. Ifstream in file, data.bean, std, ios, binary. If the file is opened successfully, we declare an integer and a double. Then we use the read function, along with reinterpret_cast and sizeof, to read the integer and double from the file. It is important to check if the read function was successful by comparing the result of count with the expected size of the data. If the read was successful, we can then use the data and finally close the input file stream. When working with structures in binary files, you can directly write and read the entire structure at once. This approach is efficient, but requires careful handling to avoid issues with padding and platform compatibility. Let's look at the code for how we write and read the structures. First, we define a structure called student, which has an integer ID, a character array for the name, and a float for the GPA. To write a structure to a binary file, we first create an instance of the student structure and populate it with the data. Then we open a file in binary mode using std. Offstream out file, students.bean std, ios, binary. Finally, we use the write function, along with reinterpret_cast and sizeof, to write the entire structure to the file. Similarly, to read a structure from a binary file, we first create an instance of the student structure. Then we open a file in binary mode using std. Ifstream in file, students.bean std, ios, binary. Finally, we use the read function, along with reinterpret_cast and sizeof, to read the entire structure from the file. Random access in binary files allows you to move to specific locations within a file to read or write data, which is particularly useful for updating records in place. There are 4 file positioning functions that are essential to random access. The seek function sets the position for reading in an input stream. The seek function sets the position for writing in an output stream. The telg function gets the current read position in an input stream. The telp function gets the current write position in an output stream. There are 3 position flags that determine the reference point for the seek operation. The ios beg flag indicates the beginning of the file. The ios cur flag indicates the current position in the file. The ios end flag indicates the end of the file. In this example, we open a file for reading and writing using std. Stream file, data.bean std, ios, binary std, ios, in std, ios, out. We move to the third record in the file by using file.seek, 200 std, ios, beg, assuming each record is 100 bytes. Then we read the data at that position into a student structure. Next, we move back one record using file.seek, -100, std, ios, cur, and update the GPA for that student. Finally, we write the updated structure back to the file. Proper error handling is crucial in binary file operations to ensure the reliability and stability of your programs. It involves checking whether files are opened successfully, handling read and write failures, and managing end-of-file conditions. In this example, we open a file in binary mode using std. Stream file, data.bean std, ios, binary std, ios, in. We check if the file opened successfully using file is_open. If the file does not open, an error message is printed to the standard error stream. Next, we attempt to read data from the file into a student structure. After reading, we check for read errors using file.fail. If a read error occurred, an error message is printed to the standard error stream. We also check for the end-of-file condition using file.eof. If the end of the file is reached, a message is printed to the standard output stream. Let's consider a practical example of using binary files to create a student records database. This involves implementing several database operations such as adding new student records, reading all student records, searching for a specific student, updating student information, and deleting student records. This application utilizes several key concepts. We use a structure to represent the student data. We employ binary file input and output operations to read and write data to the file. We utilize random access to update student information in place. We also implement error handling to ensure the robustness of the application. In this code snippet, we add a new student record to the database. We open a file in binary append mode using std. Offstream file, students.bin std, iOS. Binary std, iOS, app. We then write the student structure to the file using file.write, reinterpret_cast, const_char**, and student, size of student. Finally, we close the output file stream. To summarize, here are some best practices to follow when working with binary files. Always check if file operations succeeded before proceeding. Ensure that you close files when the operations are complete to free up resources. Use fixed size structures for predictable access and to simplify random access operations. Consider platform compatibility, particularly endianness, to ensure that data is interpreted correctly across different systems. Implement error recovery mechanisms to handle potential issues such as file corruption or read/write failures. Use exception handling to create robust and maintainable code. Document the file formats for future maintenance and to ensure that others can understand how the data is structured. Here are some common challenges you may encounter when working with binary files. Cross-platform compatibility issues can arise due to differences in data representation and endianness. Handling variable-length data efficiently requires careful memory management and data structure design. Ensuring data integrity during crashes involves implementing mechanisms to prevent data loss or corruption. Managing file size for large datasets requires efficient storage and retrieval strategies. Implementing efficient search algorithms is essential for quickly locating specific records within a large binary file. Dealing with file corruption requires implementing error detection and correction techniques. Balancing performance and flexibility involves making trade-offs between execution speed and the ability to adapt to changing data requirements. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.